So I'm going to talk about the GPU architecture. Okay, so let's start from the GPU programming and GPU assembly and GPU core design. Now, although we're not going towards that low-level detail for like to a circuit level, but I will just use block diagram to show you how GPU works internally. I'm more familiar with AMD architecture, but I will also bring up something I know about NVIDIA architecture. Then it's not very different. The core idea are pretty much the same. But the detailed design are different. Then we'll talk about their differences. Now I will use 2 to 3 lectures or even 4 lectures for the rest of the semester to cover GPU architecture. I don't know how many I need, but I will teach as we go. So how many of you have written GPU programs on your own? 3, 4, 5 CUDA programs, right? When I say GPU program, it's CUDA programs. Now you basically know how CUDA programs work. So, but many of you have never written a CUDA program. So let's start with this big part called GPU architecture. But start the first part with CUDA programming. Then for CUDA programming, you may also ask, since we're teaching AMD architecture, why I'm teaching CUDA programming, because CUDA programming is mainly for GPUs, right? Then it's for NVIDIA GPUs. So AMD starts with a program framework called OpenCL. Now OpenCL is an open standard that every vendor can implement. Then it's a trademark that actually belongs to Apple. Then Apple is now using OpenCL, AMD is not using OpenCL, then OpenCL is not very popular these days. Not a lot of people are using OpenCL. Then since I said AMD is not using OpenCL, then what AMD is transferring to is a program language called HEAP to replace OpenCL. And the design idea behind HEAP is to make it as close to CUDA as possible. So basically, AMD provides this software called Heapify. Heapify is a software that can automatically convert CUDA program into a HEAP program. That is pretty much 99% of the work can be done with a search and replace. Find CUDA and replace with HIP, then the program should work. Okay, so whenever you learn CUDA, you know HEAP programming. So for AMD architecture, I'm not going to teach too deep into CUDA programming, but basically let you know the basic principles of how to write a GPU program and see how this program is designed to fit their architecture and how the software and hardware maps together. Then CUDA programming include 2 parts. Then since we're talking about this thing called heterogeneous programming, then when we say heterogeneous programming, we say 2 different devices or different devices work together. For a very, very long time, when people say heterogeneous programming, it equals to CPU plus GPU programming. So these 2 devices are used together. And today, when we're talking about heterogeneous, we may talk about other accelerators, but for a very long time, we only refer to GPU programming. So whenever we say GPU programming, it pretty much equals to heterogeneous programming because GPUs cannot work on its own. There has to be a CPU that controls the GPU. Okay, so then in this case, we have 2 devices. So we need actually 2 languages to program both the CPU and GPU so that they can run in different way because they have different nature of their hardware design. So one single set of program cannot control both of them. So CUDA then can be divided into 2 parts. One part is called the host part. One is called the device part. When we say device is the GPU, when we say the host is the CPU. So 2 parts of the program that we need to write both of these 2 parts. Okay, so then let's see how we can write this type of program. Then CUDA program is basically nothing special but a regular or slightly modified C or C++ program. Okay, it's a extension for C and C++ language definition. So at the beginning, I will skip the include part. Okay, so then we can write int main, right? A main program. Now in this main program, now we start to execute here, right? So in this main program, what do we do? Let's write a very simple vector add example. Okay, in this vector add example, we can start by doing a float a. So by the way, when I say vector add, I'm saying element-wise add. Okay, so if this is one vector, this is another vector, then we're doing this type of like index 1, index 0, index 0, then sum them together and store it to index 0 of C. Okay. So we start with a float pointer. Then we start with float pointer A, pointer B, and pointer C. Okay. So treat my code as pseudocode. Don't think it can be grammarly correct. Okay, it's just the idea. This is how GPU programming works. So we have A and B and C. So here, when we have a floating point, when we have a float, start A and B and C, we're not saying if it's on the CPU side or GPU side. We don't know. Okay, then GPU strongly prefers floating points number. So there are different type of floating point number. We have talked about float 34, and there's a double precision that's float 64. So GPU strongly prefers float 32, and CPU strongly prefers 64, double precision. So if we're writing a GPU program, very likely we write float. Okay, so float A and B and C. Then also we likely to define a DA, DB, and DC. Then this is a convention that we start with a D. That means this buffer or this this part of memory is going to be allocated on the GPU side. Okay. Then sometimes you may see HA, HB, HC, but it's just if we want to follow that convention or not. It's really you can define these variables as whatever you want. Then for A and B and C, we write something like A equals malloc. Then malloc what? Let's say size, okay? Multiplied by size of float. Okay, we malloc something. Now when we say malloc, this is a memory allocation that is on the heap and is stored in the CPU memory, right? Now, if we want to allocate into the GPU memory, what we do? We do this. Of course, we need to allocate B and C, okay? We do DA equals CUDA malloc. Then size multiplied by size of float. Nothing special, but here we use a CUDA malloc. Now CUDA malloc is a CUDA runtime API. Okay, so it actually, this is a library call that is being executed to, like, it's calling a function implemented by NVIDIA. Now NVIDIA, the CUDA library provides the implementation of CUDA malloc, and what it will do is allocate a part of memory on the GPU side. Now it will return an address to be stored in DA. Okay, and similar to DB and DC. Okay, then in this case, this is the way using CUDA runtime API is how we can write a host program. This is nothing special but a regular C program only to call CUDA programs. Okay, then assume DA, DB, and DC are also allocated, and also we set the we use a for loop to set A's value and B's value, right? Just assume there are some values there. Then to make it work, we need to copy the data from the CPU to the GPU side. Right? So CPU and GPU are two different devices, and they're connected using something like PCIe network. So we have this is the CPU, and this is the GPU, and they're connected with some sort of networks. The CPU has its own memory, and GPU has its own memory. And until somewhere like 2016, then there are some support for GPUs to directly access CPU's memory, like using unified memory. However, it's not a mainstream. It still suffers from performance penalties. Like if you access the CPU memory, it's still not as high performance accessing the memory, accessing local memory. So what we do is we need to explicitly copy the data from here to here. Okay, from the CPU side to the GPU side. In this case, we do a CUDA memory copy. And as we know, memory copy typically have this type of convention that it starts with the destination. In this case, that is DA, right? Now we copy from A, right? Then size, I will just write size multiplied 4, okay? So that is size. And also we need to tell what's the direction we're copying, because CUDA cannot really easily tell if this is a device pointer or a host pointer. In this case, we need to provide another parameter called CUDA mem copy H to D, host to device. Okay, this is there's a constant value just tells this API what is the direction that we're copying this memory. Then CUDA memory copy H to D. Then there are two other directions, right? There's a D to H and there's a D to D. I don't think you will need H to H. H to H, you can use the regular C standard library and do memory copy. So here they provide these three, as the basic CUDA part, provide these three directions. Okay, so then we need to copy DA and we also need to copy DB, right? Now we copy the DA and DB. After this point, we have the data ready. We can let the GPU to do the calculation. Okay, so to let the GPU do the calculation is basically by calling a GPU function. And calling a GPU function, in this case, this GPU function is called a kernel. It's called a GPU kernel. Now when we say, so not all the GPU functions are GPU kernels. It's only the function that you will call it from the CPU side are called kernels. Okay, and a specific term here is not calling a kernel, but to launch a kernel. So we start a kernel on the GPU side. Now how do we start a kernel? It's basically in the same way of copying memory, of calling a function, but with some special parameters. So how we call this one? Let's say if our kernel is called vec add, okay? Now we just do vec add. Now here we need to provide some extra information, and this extra information is provided in these three special angular bracket. Now after that, we provide the arguments. So what's the argument? It's it's not A, it's DA, DB, DC. DA, DB, DC. Okay, then what else? And the size. How many elements that we need to copy into the like we need to do the add operation and to store in the destination. And this is a vector add. So before we talk about the parameter here, let's see how this GPU function is written. Okay, Then the GPU function is written in this way. Need to check a reference. Okay, the GPU code is written in this way. It typically starts with a global. It's a preamble. And it says this is a GPU kernel program to be compiled into GPU format. Then we can do a void. It cannot return anything. A GPU kernel cannot return anything. Then all the return value has to be contained in a memory so that later on you can copy back to the CPU side. Then a void, then we can call it a vect add. Okay, then there's nothing special. Here we write float. I'll write it into the next line. Float star A, float star B, float star C, and size. Okay, a list of parameters. So nothing special, but just as if you are writing a CPU program. So the GPU compiler, the compiler will just tell, okay, it's checked that's a global, right? If it's a global, that it has the potential to be run on both the CPU side and the GPU side. And if it's a device, then it can only be run on the GPU side. So it will only generate a copy of the binary that is for the GPU. Now in this case, we need to run this part of the program. So the key point for GPU program is, say, you write one function, and this function is only for one thread, is to run on the GPU side. So then you need to consider what is the responsibility of this GPU thread, right? So what do you want this GPU thread to do? Then an easy way to consider this problem, since we have a vector add example, then we are adding these numbers together, right? We're adding these numbers together. So there's no interference to calculate this part and this part. So they're totally independent, right? In this case, we call it an embarrassingly parallel pattern. So this pattern is called embarrassingly parallel because it's just so easy to make it parallel. Then almost there's no need to do any optimization or any special type of work. Then we can make it special work. It's a basic element-wise operation, right? In this case, the simplest way to write this program is to let each thread to be responsible for one number, one output number, right? So even for more complex GPU program, very straightforward to think about how one can organize this thread is to consider each thread is responsible for one region or one piece of output. Okay, then in that way you can make them like the calculation as independent as possible because you don't want threads to communicate. Any communication or synchronization is has a performance penalty. Okay, so then we say we have defined, so thread 0 will do this, thread 1 will do this, thread 2 will do this, and so on, right? So in this case, if we have n element, then we need n total threads, right? So when we write this GPU program here, we need to consider these threads needs to know what's my index, who am I, then I can do the right task. I know, oh, I need to add these particular numbers, right? So the GPU needs to know what's the number. So in this case, we will typically first to identify itself. And in this case, we have typically start with knowing my own ID, and I call it GID, global ID. Then which part is not global. We'll talk about that later. Then GID, it needs a little bit of calculation. So what's the calculation is basically in this way. Block index ID x dot x plus block dim dimension dot x multiplied by, sorry, this is not plus, this is multiplication here. Then plus thread ID x, thread index dot x. Okay. So a quick way that you can think about this problem is there are two dimensions here. One dimension is block. One dimension is thread. A block is a group of threads. So you can consider this way. Say a block may have 256 thread, right? So my local thread ID is 0, 1, 2, and so on, then end with 255, right? Then the next one, the next block also has this thread ID start from 0, 1, and 255. So what is my global ID then? My local ID is 0, 1, 2, right? My local ID is 0, 1, 2, 2, 255. Then what is my global ID is basically by knowing my block ID. So this is my block ID 0, block ID 1, block ID 2, and so on, right? So to multiply by the block dim is 256. The block dimension, 256. Then by multiplying this number with 256 plus the local ID, we know my global position in the whole kernel, right? Like the thread ID within the whole kernel. So this is my global ID. Then, okay, with this global ID, I know which element we need to process in the vector, right? Now we need to do the calculation. In this case, we simply do a C square bracket C GID equals A GID plus B GID. Okay. Then of course you need a little bit safeguard so that what if your size, what if your kernel size, number of threads is larger than this size? And what you do is simply do a if GID is greater than there should be another way to calculate the kernel size. I will simply write kernel size here. If it's greater than the kernel size, no, not kernel size, not really kernel size. It's only this size. It's the vector size. If the GID is greater than the vector size, so if this is the vector, we're accessing somewhere here, somewhere like passing the end, we simply return. We don't do the calculation. Okay. Otherwise, we do the calculation. Okay. It's just a safeguard to prevent us from accessing the passing the end of the boundary of the vector. Okay. So then at the end we return, or we just silently return. That's the very simple kernel that we can write. Then as you may notice that there's a block ID x and block dim x and the thread index x, right? So for most of the time, we write one-dimensional kernels, but sometimes if we're dealing with a matrix or 3D volumes, then it's more convenient to have 3 dimensions of this kernel, of this thread. In that case, we can have 3 dimensions of this kernel. In that case, we'll have block index y, block dim y, thread ID y, and so on. Okay. Then this is a kernel. This comes to this part as how we call this kernel, how we launch this kernel. We say a kernel is written for one thread. Then it's the host program's responsibility to determine how many threads are there. Now how can we do? Is we need to provide two numbers. The first number is we call it the kernel size. Then the second one is block size. And kernel size is in terms of how many blocks are there. Okay, so roughly speaking, we can say kernel size equals to n divided by block size. Okay, then however, you need to do round up. Okay, you need to do a round up so that we never have some left over. Let's say if your block size is 256, then if your n is 300, right, then you always want the leftover 44 to be taken care of. In that case, you always want to round up. In that case, you won't have two blocks. One block is not enough. One block can only process 256 numbers. Okay, so of course, these two lines of code needs to be called before vector add. Okay, now here we just need to write, I'll write it simple. Kernel size and block size. Okay, just to specify how many threads you want to launch. Okay, then for block size, typically we do somewhere between 64 to 1024, and we typically do a multiple of 64, or very likely we do a size of power of 2. Okay, either 254, 512, or 1024. And it sometimes matters a lot for the performance, but at this stage, we're not diving that deep into GPU performance optimization. We just want to say you can just 256 or 64 are probably the most common numbers that we take. Okay. Then at this point, we can return. We know we're running this program, and this program in CUDA definition is a asynchronous call. That means when after calling this function, we immediately return without waiting for it to complete. In that case, we can let the CPU to do something else while the GPU is running. So how we can make sure this one is completed? In this case, we call a CUDA device synchronize. And we call this function to guarantee that we wait for this kernel to be fully completed. Then at the end, we can do CUDA mem copy. Now we copy into C from DC, and with a size multiplied by 4 and the direction of CUDA mem copy. And this time is device to host. Okay, so now we copy the result back, and for the rest of the program, you can just use it however you want. Okay, it's a GPU program, how a GPU program is written. So no matter how complex GPU program that you are writing, it's basically this way. Copy memory, let GPU to compute, then copy the data back. And then all the way it can goes up to ChatGPT in this level of program. Is all start with these basic things. Okay, so this is a general way of how we write a GPU program. I think the most important part is the threads are written in a way that that each thread is responsible to calculate one piece of output, and the threads are rarely communicate with each other. And there's a strong limitation in the GPU how the threads can communicate with each other. Okay. So this is not a GPU programming course, so I want to quickly go through this part and jump to the GPU assembly. And let's see how the GPU assembly is different from the CPU assembly. Then I want to show you one even simpler program. Okay, this program. I will erase this part. And I call it shifted copy. And takes float in and out, two arguments. Okay, and it's super simple that int gid equals to the thing that we write before. Okay, then out gid equals to in gid plus 4. The smallest program, right? So I just want to show you how this program is compiled into a GPU assembly and what the GPU assembly looks like. It doesn't have a safeguard here, so we just show it the compilation. Then the GPU is different from the CPU. CPU needs to set up the memory at the beginning to set up the environment so that the core can pick up from the memory. The GPU, because you have the CPU to control, and CPU send this task to the GPU side. So GPU internally will have circuits to help up set the context. And the GPU try to avoid the memory access, and only if something can be in the register, it's better to be in the register. So the GPU will typically have some initial register layout set up so that it's being stored there. So in this case, the first line of code is like this: s load d word by 4. Then s03, s45, and 0. Okay, so we need to look at this instruction. Load is load. It's still the load that we're familiar with. Okay, we load from memory and store it into a register. Now, what is S here? So S is a term only for AMD GPU. NVIDIA doesn't really have it. Then S here represents for scalar. And on the other side is a vector. Okay, so in this case, it's a scalar. So GPU programs work in this way. Remember, we're talking about blocks, right? So a kernel, this is a kernel. And a kernel can be divided into a few layers of different things. The first layer is block. Within block, we have warps, W-A-R-P. Okay, within block, we have warps, several warps. Now within warp, we have threads. Those are all threads. Within each warp, we have threads. So there are several layers of organization. When we have this organization, there are some meaning of this organization, why we want to organize it in this way. Okay, so but I want to give you a typical number. A warp equals to 32 threads. in NVIDIA. In NVIDIA GPU. Then it equals to 64 threads in AMD CDNA architecture, and also equals to 32 threads in AMD RDNA architecture. Okay, then so AMD has different standards. Now RDNA is mainly for graphics, and CDNA is mainly for compute, right? So by the way, when we talk about GPU architecture here, we're only talking about GPU, general purpose GPU computing. It's not talking about rendering graphics and these type of things. It's only for calculation. So a warp is this number, right? Now remember, when we talk about block, is typically 32 to 1024 threads. Okay, then a block is 32 to 1024 threads. That means it equals to from 1 to, let's say, if it's 32 by how many is 1024? 32 by 32 is 1024. Okay, so now a warp is this number, right? So a block equals to from 1 to 32 warps. That's a typical range. Then one level up, a kernel equals how many blocks? Then typically I would say this is unlimited blocks, right? Remember last time we're doing a vector add example. Then the number of threads is equals to the number of elements in the vector. So it can work if it's 1 giga element. So in 1 gigabyte element, that's a lot of threads, right? And your kernel can still run. So this number is a rather flexible number. The number of blocks in a kernel is a rather flexible number. So you can see when we launch a kernel, how many threads we start. Like we can start 1 billion threads. No problem, GPU can handle that. Now, of course, it cannot handle it, like run them all at the same time. So there's one way to run them in different ways. So then, why warp is so important here? Then when we program, we only program blocks and threads, right? We only know like the two numbers we give, like the kernel size is the kernel size in terms of number of blocks, and the block size is the block size in terms of number of threads. Then, but this idea of warp is recently added at this stage, only at this stage. So warp is not a, I would say not an architecture or something that a programmer should be constantly aware of, and it's only at the microarchitecture level or the implementation level. Then it's not that pure at the implementation level. Sometimes programmer needs to aware it for performance tuning, but it's not that important at when you write a program. So why is warp important is because the GPU runs in a very special way. GPU runs program in a, we call it a SIMD style. A SIMD style is for single instruction, multiple data. Okay? Single instruction, multiple data. Then what does that mean? I can write the next instruction. You will know what is single instruction, multiple data. This is a V, so it's a vector, right? It's a vector, and what do we do? Is shift left. It's L. It's logic shift left. REV. You can ignore this REV. This REV allows the operand to be written in the other way. Then B64. So this is a 64-bit operation, okay? Then what's the register is V, 2, 3, 2, then V, 2, 3. Okay, this is the operation. So first of all, what is V2? V2 is a So V anything is a 32-bit register. Okay. So when we say V23 is a 64-bit register combined by 2 registers. So it's a number that is connected in 2 adjacent registers. So this is 64-bit. Then this is shift left. So basically it's the value that is stored in V23 and shifted by 2 and stored back to V23. Okay, shift left by 2 digits, that's multiplied by 4, right? So it's a multiply by 4 operation. But how many multiply by 4 operation that we actually calculated? Whenever this line is executed, since a SIMD instruction, a single instruction, this is a single instruction. Then when we talk about V2 or V23, then within a warp, you have thread 1, thread 0, thread 1, and so on, and thread 31, right? So this one may have a value that is 2. This one may have a value of 6. This one may have a value of 8 and 13 for example. Okay, so every thread within this warp may have different values. So they have different values, right? It's the same. We call it V2, but even in the CPU program, a different thread, the same name, the register with the same name storing different values because they run in different cores, right? So V2 have different value for different thread. In this case, when we do shift left, then the end up V2 value will be 4, 12, 16, 26, and so on. Okay, so that's what is called single instruction, multiple data. Okay, so this is why GPU is super powerful, because it takes this thing called data level parallelism. Okay, so that we can calculate all this data at the same time. So whenever we calculate a shift left, we calculate all 32 threads at the same time. So consider in CPU, we run fetch, run decode. Now after a fetch and a decode, and we execute one instruction, we can do one calculation. Then we write back one value, right? In GPU design is in this way. We fetch one instruction, we decode one instruction. We do 64 or 32 or 64 calculations, depends on the warp size, right? So that the average cost for decoding, control, and for fetching an instruction is much lower, because you fetch once, you decode once, and it applies to 32 numbers. Per calculation, your fetch and decode cost is much lower. That's why GPU can really put a lot of resources only on compute and can make the control flow really simple. Okay. Then other than SIMD, then you can think all 4 different combinations, right? So you have SISD, you have MIMD, then you have MISD. Okay, multiple instruction, single data. And this is possible. Then we want to, like, say, one piece of data, then in one cycle we want to process multiple operations, and all these things are possible. Okay, that's SISD, a typical CPU architecture is considered SISD. Then MISD, if you consider multi-cores, are SIMD. Okay, right, multi-core. So if each core is running different instructions and they're processing different data, so the instruction and data are not related. Then other than this term, if you read papers, you may also see other papers saying GPU is something called a SIMT SIMT structure. T here means single instruction, multiple thread. Okay, so because we have multiple threads, and then in theory, this is more suitable for the AVX instruction set. If you know what is AVX instruction set, yes, this is CPU extension for vectorized operation. Then GPU is more SIMT style because each instruction is controlling multiple threads. But I don't want to tell very different. Like if you say GPU is a SIMD architecture, everyone will agree with that. Okay, just someone will use this term, someone will use this term. Okay, so then what is a vector and scalar? Come back to this point. A vector is really a SIMD instruction. So we really are doing 32 or 64 operations within one instruction. But sometimes all the threads are doing the same operation. For example, load, in this case, we can load the same thing. We are really only loading the same thing. And what is loading here is actually loading, I think it's loading this thing, if I'm right. Yeah, it's loading these things. So it's loading the in pointer and out pointer. In this case, we have a scalar instruction. In this scalar instruction, we use a special scalar unit to say, oh, I only want to run one operation for the whole 64 threads. And that comes to these S registers. So S registers are shared within a warp. Okay, are shared within a warp, not a block, are shared within a warp. So they say, here we say within a warp, then I need to change here. For S2, okay, T1, you are storing value 2, T2, you are also storing value 2, and they're all value 2. Okay, they must store the same value. And actually, in hardware, there's only one register there. So it's a shared register space that everyone can use. Okay, that's a scalar operation. In this case, what we're doing, so you see, we start with accessing S45. And S45 is kind of hard-coded at this moment because we know the hardware will start this thread with a register value already set. What is storing? I think it's storing a pointer to this region of memory that is called kernel argument. And it's basically using 4-byte or 8-byte to store this register to this pointer and 8-byte to store this register. And see here, GPU wants to do parallel operation, right? In RISC-V, we load one word. Now here, we're loading double word by 4. Well, that's why I say I hate the term of word. Then in RISC-V, when I say word is 32-bit. In GPU, in AMD GPU, a word is 16-bit. So double 16-bit. So D word, double word, is a 32-bit value. So we're loading 4 registers at the same time with one instruction. Then basically we'll end up with S12 with 0, 1 is flowed in and S1, 2 is flowed out. Is okay. So just load all them together. It's an optimization rather than using 2 instructions to load them. Okay. So I can I think I can skip some instructions and directly jump to the most important part. Wait, let me introduce this one. I think this one is important. The next one is an S wait count. CNT, wait count. Okay, it's waiting for a counter. And I really hate this name. LGKM CNT 0. This is AMD assembly. Okay. So what does it mean? And let me write down the next one. As ADD. Oh, this is finally something that we're familiar with, right? U32 S0 16 S0, as ADDC U32 S1 0 S1. Okay, so you can see there's a dependency. What is a dependency? Is here this value and is being used at here, right? So there's a dependency here, right? And the lecture that we should talk about today is to talk about the dependency in CPU architectures. But here in GPUs, we also have this dependency. And there's no dependency in this line of code. V23 are V23, and they can just do it on their own, right? So V23 multiplied by 4 has no dependency with this line of code. So how AMD GPU is handling this one is this instruction is executed, and when it's executed, it will send some request into the memory system. So GPU memory system is much more slower than the CPU memory system, and you cannot really set the memory as one cycle, as one pipeline stage. It has to send some requests out and wait for some time until the result will come back. Okay, so in that case, this instruction may take very long time, hundreds of cycles possible. Then we may have some opportunity to execute the next instruction, right? We may have the opportunity before this data to return, we can start to execute this line of code. Then we run this line of code while waiting for this to return. Okay, but if we execute this line of code before this data return, we may use some garbage data. In that case, we have to make sure that this data is returned. So when we send out a load instruction, when we send out a load read request to the memory system, we add this counter by 1. Okay, now when this data returns, we reduce this counter by 1. So waiting to be 0 means we wait until this counter to fall at 0 or below 0. And of course, for 0, it cannot be below 0, but if it's a real number, it can be below that number. Okay. So in this case, this is a compiler-added synchronization. Say, at this point, we have to wait the prior memory access to return, then we can continue. So this is a synchronization. Okay, so with this synchronization so by the way, what it does is basically S0, 1 plus 16 and store it back to S0 and 1, right? So ADD do not consider carry. ADDC consider carry from the previous instruction. Then it's adding 0 is only for the carry, just in case the carry is non-zero. Okay, so these two instructions add is the 64-bit add instruction. So use two instructions to mimic a 64-bit operation. Okay. Then let's keep going. Let's assume we have all the addresses calculated. We know the addresses that we need to calculate. So the next thing is we need to load the data. In that case, AMD uses something called the global load. Then in earlier version, you may also see something like flat load, but let's just use global load here. Global load D word. And where we're storing in V4 and our input is V0 and 1. No offset. Then you see, if it's an S instruction, it can only use S register. If it's a V instruction, it can use both S and V register. In that case, although it's not saying if it's a V or S instruction, since it's used the V register, it's a vector load. Okay, vector load means every thread may have a different address. Now, if this is a warp of 32 thread, we may be issuing 32 memory read requests to the memory system and wait for 32 pieces of data to return. Okay, so you see the amount of memory transaction that GPU loads a lot of memory and calculates a lot of data and store a lot of data back to the memory system. Okay, so and eventually the result is stored in V4. Then interesting thing happens here is there's a vmove, there's a VADD, and there's a VADDC. I will not write the full instruction, but I can tell you this is calculating the output address. Okay. Then these instructions, since we're calculating the output address, they have nothing to do with V4. V4 is the data that we loaded. So we can, before this one to returns, we can just do the calculation, right? There's no dependency. Then here we do S wait count. In this case, we're waiting for this counter called VMCNT. So VM is for vector memory. LGKM is for local global constant memory. So they share, this different memory system shares one counter. So you can consider this way. S load uses this counter. V load uses that counter. Okay, so different counters. Then we don't need to do calculation. Eventually, we do a global store. Remember, this is a simple. Like a data movement kernel, right? So we can do global store, dword, v4, and v0 and 1. So v0, 1 stores the new address, the destination address, and v4 is from here. So we directly store. Okay. So then we're done with this program. At the end, we always add an instruction, a scalar instruction called end program. Okay. That's basically how this type of kernel is implemented. Okay, any question? So I think the most important part is the difference between vector and S instructions and the use of S wait count and why S wait count is used here. Right? And question?
Wait, you said NVIDIA doesn't have scalar and vector instruction?
Yeah. So NVIDIA doesn't have scalar and vector instruction. Just consider all the instructions are vector instructions. So they don't mind just do it for 64 times. They think a simpler core design is probably more important than this clever optimization. So they just do it for 32 times. It's probably not that bad. Okay. And I'm not sure that NVIDIA has something like S wait count. So this needs some work to understand how NVIDIA do this. And I never dived that deep into NVIDIA microarchitecture. So I don't know how they handle memory access synchronization. Okay, so S and V and the Y wait count is added is the important part for GPU architecture, and especially the difference, especially the concept of SIMD instruction is the most important thing that you need to remember. Then let's do this. Just make this program slightly more complex. Now I know what you're thinking about, how we can handle conditions and how we can handle loops, right? So loops are easier, conditions are more difficult. Let's consider this kernel called condition copy. Okay, then condition copy, we still have in and out. And in my example, I'm using double here, although it's probably not that important. Then still I have an int GID, global ID, that is calculated by that expression. And here we want to write if in GID greater than 0, then out GID equals to in GID. Then if we know the output is initialized to be 0, this is pretty much a ReLU implementation, right? So let's see how this one is implemented. Okay, so we will skip this part. At the beginning, it's the same. Okay, we'll skip this part to calculate the address. Let's directly jump to here. So here, let's see, we start with a global load. In this case, since in my example, I'm using double, let's do d word multiplied by 2. So that's a double number. Okay, you can do d word multiplied by 3, d word multiplied by 4. So GPU is really providing the flexibility that with one instruction, you can load a lot of data. Then it's stored to v45 from v01. Okay, the destination is stored in v5. Now here we need to do a comparison. Now, of course, before we do the comparison, we need a S weight count. After the data is there, we can do a comparison. Now here a comparison is SV CMP compare less than. Now here we have a type that is XF64, so a double precision comparison. And comparison, we store the result into a special register called VCC. VCC is only 64-bit. Okay, so assuming one warp is 64 threads. In this case, if it's less than, this bit will store to be 1. This bit, if it's smaller or equal to 0, this bit will be 0. So it's basically a bit mask to store the comparison result. So the destination is VCC, and we have 0 and V45 just to make the comparison. Okay. Okay, then next thing, the interesting thing is here. This instruction is called S and save exec. B64. S45 VCC. Okay, I'll explain this. Ignore the AND for now. And probably for the class, just look at exec. Exec is a special register. Then it's equals to the warp size. So in AMD, in CDN architecture, is a 64-bit. In NVIDIA, is 32-bit register. Okay, so here, you know, last time we were talking about this runs in a SIMD execution style, right? So that means we just assume this is one instruction. Now, if this is a one instruction or few instructions, if one thread needs to execute it, all other 32 threads, all other 31 threads are also executing it at the same time. But we don't want these things to happen, right? We don't want the other 31 threads to really take effect. if they take effect, they will get a wrong result, right? So what we do is we use an execution mask. So this execution mask is a mask. Let's just make it 32 thread. Then you can have some ones there and some zeros in this execution mask. Okay. Then this one is mapped to thread 0, thread 1, thread 2, and so on, thread 231. Okay. If this bit is 1, we make that instruction take effect. If it's 0, we'll just skip the memory part and the write back part so that it will not take effect. It will not impact the execution result. Okay, it will not impact the result. In this case, what we're doing is we're saving the execution mask temporarily into S45, and actually is there's an AND operation. The execution mask is stored here, then there's an AND operation that the current execution mask will do an AND with VCC. Why we do AND is basically just consider nested if, right? We already have something that we say is 0, then we will do AND, we'll mask out some other cases, right? So that's why it's an AND save execution. But what I can say here, just make it simple, we store the VCC value into execution mask. Okay, we store that value into execution mask. So then this one becomes a value dependent execution mask. And there may be some 1s and some 0, some 1, some 0, some 1, some 0. That really depends on the value, right? Then there's a chance that all of them are 0. If all of them are 0, we don't need to load and we don't need to store. We can just quickly, we don't need to store, we can just quickly jump out, right? So then we can do a quick conditional branch, and it's also an S instruction. It's an SC branch. SC branch EXECZ. Okay, that means when the execution mask is all 0, we take this branch. Okay, there's only one operand, and this operand is BB0_2. Okay, it's a basic block 0-2, 0_2. Okay, so this is AMD compiler always generate this type of labels. So use basic block labeling. We'll write the label later. Okay, so here we're done with this part. Then we do we move, we add C. Those are not that important to calculate the destination address, right? Then eventually we do global store, and it's not important also. dword. Why is dword? I think it's dword by 2. Now we store the result back, right? And I'm not showing the operand. It's easy, it's trivial. And also, just be careful. When we talk about store, there's no wait count, right? Just consider we're sending out stores and we don't care anymore. So there's no synchronization. Just they're in the buffer, in the queue, and probably even the next kernel started, the write is not completed yet. So GPU tries to optimize for every optimization opportunity. So in this case, the store, there's no synchronization. Okay, now here we finally have this BB02. Then there's an S or B64. And what is it? Is EXEC S45. And also don't think too much. EXEC is mask, right? And we store the previous exec in S45, right? We do an OR operation, is basically recovering the execution mask right before the condition, so that we can, if there are some instructions, we'll continue the execution. Okay? There's some instruction will continue the execution. So we just restore the execution mask. In this case, we just set it to all ones. That's why it's an OR operation, bitwise OR operation. Then at the end, we say S and PGM program. Okay, then that's the whole program. So I want to tell you that GPUs uses an execution mask to run a predicated execution. What is predicated? Predicated is an execution style that uses one bit, 0 and 1, to decide if this one instruction will take effect or not. Then this is not only used in CPU, it's also only in GPU, it's also used in CPU. So sometimes it's just for compiler simplicity. You can simply set this bit to 0, so this instruction is there, but we don't want it to take effect. This is called predicated execution. GPU uses these masks and predicated execution to handle branches. Okay, so in GPU, there's a very special situation or consideration for performance analysis that is called thread divergence. Okay, so what is thread divergence? Is that let's say if we only have 64 threads in a warp, okay, in a kernel, then if we write something like if TID is smaller than 1, okay, in this case, 1 out of 32 threads are effective. But the other 31 will still take the computational power, will still take time. Okay? And it's a totally bad thing. We'll talk about how it works, why it cannot be easily optimized out. The newer NVIDIA GPU has some way to allow different threads. Say some thread is running one branch, some thread is running on other branch. AMD GPU still today, as far as I know, do not have that technology. Then, in this case, if our computing power is something large, then we only have 1 over, it's like to have somewhere like 3% of utilization, right, in that part. Now, if you have something like, if TID is smaller than 16, then we have 16 over 32 that is available. In that case, we have 50% of utilization, right? So thread divergence means the threads within a warp is going on different routes, which is considered a bad thing for GPU because we're underutilizing the GPU capability. So if we can avoid that and to somehow ask a GPU to let the GPU to run on the same path without diverging, it's always a good thing. Okay, so thread divergence is a big performance issue for GPU, and there are many different optimizations, especially in the compiler world, to reduce thread divergence. Okay, so probably say one warp is, say half a warp is going this way, half a warp is going that way, but for next warp, half a warp is going this way, half of that in that way. So can you combine this half warp and that half warp together, right? In that case, we avoid thread divergence. So there are many like academic research that is doing this type of optimization. And for industry, there's always a problem that we really know very little about how NVIDIA GPU works internally. There may be some optimization, maybe not. No, we don't know. I'm pretty much sure this is a so classic issue, then there's some optimization in NVIDIA GPUs. Okay, I hope you like this type of Blackboard-based teaching. Then For GPU, I'm pretty much like, I hope for the next few Thursdays, I will try to in this way to teach GPU programming. Okay. All right, I think that's all for today's lecture.